Welcome everyone to the 3 Rand workshop. It's a Web3 Randomness Workshop. For short, we call it 3 Rand. This is the first day. Very excited to host this. I, along with my co-host Aniket, myself, a senior director of research at Supra. Aniket Kate is my co-host. He is an associate professor at Purdue and a chief research officer at Supra. And I'll give a very brief introduction. It's non-technical, just give some sort of bullet points for motivations and some nice facts. If you're into like more research, this will be like there will be some nice facts. I talk about gaming industry and so on. So I know that randomness in Web3 has different applications, right? You can think about, some people are more familiar with applications such as using randomness to select a leader in proof of stake mechanism or some other ways. There are different mechanisms. But which one is the most emerging use case of Web3 randomness? That is Web3 gaming, or in short, it's called GameFi. And I found this nice excerpt from this blog by Entangle. There they talk about the GameFi landscape and its potential, right? So if we go back to Web2 gaming landscape, like this traditional online gaming, which boasts of 2.7 billion users annually. So basically, like more than a quarter of all people, actually. It's mind-blowing facts, right? And is expected to bring 4.90 billion by 2023. And there are like entire ecosystems like online gambling marketing with like huge amount of revenue coming and so on. And Web3 gaming, however, has some benefits, right? So for example, there is this Web3 gaming app called Hackjack, which is basically a Web3 blackjack game, right? Where the players can earn NFTs based on the results of the game, right? So traditional Web2 gamings are a bit different. So you are attached to a particular platform. If you earn some reward, you stick to that platform, right? Web3 gives you opportunity to earn some sort of actual NFTs, and NFTs you can basically use them across other platforms. For example, here they allow NFTs to be sold on Zora Marketplace. And any kind of this gaming, good randomness is actually very crucial, right? I think there was one slide missed. Okay, so this slide was somehow skipped. So let me just talk about this slide. So I wanted to make a few points about what's special about Web3 gaming than Web2. First of all, there is this model called play to earn, right? So if you play in Web3 gaming, you can earn rewards in the form of actually true assets like NFT. And if you own an NFT, that has like a true asset. Like if you have a digital signature, you own that entire NFT. And then I think I already talked about, like there's this marketplace option that if you take one asset and it's interoperable, that means you can take one asset from one ecosystem and go to other platform. That's like a huge flexibility. So that's why Web3 gaming has this huge sort of potential. Some of this slide was switched back when I was sleeping, but I don't know. Anyway, so the point I wanted to make, and this entire gaming, as you can imagine, like blackjack, poker, I'll be talking a little bit about, there is a talk afterwards in the workshop. Good randomness is actually essential, right? So it's a lot of the fairness of these gaming applications rely on source of good randomness. So I'm not going to explain what exactly good randomness means, right? So I think over the course of this workshop, it will be explained in more technical details. For beginners, good randomness means like you need properties like it cannot be biased to certain things for fairness, of course. It cannot be predicted ahead of time, right? And these two properties should be verifiable by anyone. So these are like a very brief introduction of what good randomness means. And you can always imagine like any kind of gaming applications, you do need this kind of good randomness source. So randomness, as we know, is a very important resource in computing as well as in Web3, especially in gaming, right? I briefly mentioned like on-chain poker, where without a good randomness, the game would not have any fairness. On-chain lottery, different kind of application. However, so I found this nice excerpt from a blog from Chainlink that if we go beyond this traditional fairness aspects of randomness, there is a very interesting aspect of randomness, especially important to games, right? So let me just read out a little bit. In his 2005 book, A Theory of Fun for Game Design, developer Raf Coaster describes a pitfall endemic in boring games, what he calls the mastery problem. So you can read this paragraph, but the entire thing that's it's trying to convey is that randomness gives you certain amount of uncertainty. That means if a game has a very deterministic nature, at some point you can master it. For example, it's I can give you some personal experience. Like when I was playing tic-tac-toe with my daughter, so now she's 7 years old, she was 4 or something, right? She used to like it. And because she was not winning all the time, or she did not know how to make it draw, at some point she actually mastered the art. So anytime I start playing, she was always like, you can find this strategy, you can make a draw always, right? Then she lost interest, she got bored. And we are like adults, like more complex species, it's easy to get bored all the time. So randomness like keeps you like dragged to a particular game. And to quote from this particular excerpt, that one key function of randomness in games is to expand the dynamism of player actions and environments, preventing mastery. So you want preventing mastery, like mastery too easily, from becoming too quickly attained and better rewarding continued engagement. That means if you are engaged, if you put enough effort, you get some reward at some point. And particularly, as I explained in Web3, if you get a reward because of this marketplace and flexibility option, basically you can sell this reward to a marketplace and basically own actually a complete virtual asset, right? So I think this is like the overall introduction of GameFi, which is, according to us, probably the most important use case for randomness on chain. Of course, there are other use cases, and over the course of this workshop, a lot of talks will be focusing on different kinds of use case. But let me just stop here and just get the program started. So let's see. Okay, here is our agenda for the first day. I just already gave the introduction. So in the first session, we'll have randomness services in practice. We'll see a randomness talk from the NIST randomness, which is not really on-chain randomness, but a centralized randomness beacons to start with. And then we'll have other randomness that are deployed like DRAND. And then Jacob from Supra will talk about there are different findings we have at our lab with deployed surfaces. Then we'll have a 15-minute break. And after the break, we'll have an industry-focused panel. And we'll talk about demand of randomness in Web3. This is very important. So that's why I actually started with these GameFi applications, because this is like one of the a killer use case of on-chain randomness. And there we discuss with different experts in industry that what is the exact requirements for on-chain randomness, are we moving towards the right directions, and so on. So after that, there will be another 15 minutes break, and then we'll have 4 talks in this randomness generation in spatial and different settings. These are slightly more technical talks involving strobe, like stake-based threshold randomness beacons, Aptos's weighted BRF, which was recently deployed. And then we'll have a talk by Guru time lock encryption, and this is related with some sort of distributed randomness. And finally, we end today's session with game theoretically fair randomness generation. All right, so let's get started with the technical stuff. And the first talk will be given by Luis Brandao. Luis is a researcher at NIST/Strativia. And I just hand it over to Luis. Luis, you can share your screen and start. Let me actually stop sharing. Oh, sorry. Before talk, I think I just want to mention that there are a few. Okay, sorry. I just wanted to just mention these things. Am I still sharing? No. Okay, let me just share. Okay, so here is a basic rules that only current speaker is required to turn on video audio. The others are optional. Audience questions are taken at the end of presentation or panel, and spamming will be strictly moderated. Will not entertain like irrelevant questions, of course. And for audience questions, there is a Q&A box you will see on your Zoom screen, and you will just use that to ask questions. So I see a raised hand. Alan, you want to say something?
I don't think he can even unmute. So maybe.
I see. Okay, maybe you can post it on Q&A and we can talk about it. So I guess I think we can get started with Luis's talk.
Okay, can you see my slides right here?
Yes. Perfect.
Okay. Thank you, Pratyai, for the introduction and the invite. Thank you also to Aniket and Supra in general. And to everyone listening, good morning, afternoon, or evening, depending on where you are. I'm currently connecting from Maryland in the US, and it's 9 a.m. on my side. I'm at NIST as a foreign guest researcher, contractor from Strativia, and most of my work is in support of various projects at the NIST Cryptography Technology Group. And one of those projects relates to randomness beacons, which naturally is very related to today's workshop. So the invite is very welcome. It's also a way for us to disseminate the NIST reference for randomness beacons. So I was asked to give a brief presentation in the context of randomness beacons, and I'll try to keep it within time, possibly still allowing for 1 or 2 minutes for Q&A. That said, I will go slightly fast. But again, feel free to reach out at any time, including after the presentation as well, if you have any questions. Let me go right into it. I've organized the presentation in 4 parts, and let me say I will share the slides in the end, and they will also be publicly posted. And there's some bonus slides in the end for offline reading with some more technical details. And for the most part in the presentation, I'll keep it high level. So I want to start with a brief introduction. And in particular, I want to clarify, because I was asked to talk a bit about NIST randomness. And I want to mention that this presentation is not about secret randomness that is essential in cryptography in many cases. And NIST, in some cases, does issue some guidelines and requirements for conformance with some crypto standards, such as, for example, randomness necessary for generating keys or secret nodes. Instead, in this presentation, I will focus on public auditable randomness. If you are interested in the first part, then you can look at what we usually call the Special Publication 890 series that includes recommendations and requirements for random number generation, entropy sources, and RBG constructions. But in this presentation, I will focus on one technical report that we have that establishes a reference for randomness beacons. Okay, so what do we consider as a randomness beacon? In a succinct sentence here with many keywords, we consider this to be a service that produces timed outputs of fresh public randomness. Let's parse this a little bit. So this is a service that periodically pulsates randomness. We call it pulsates because we sometimes call beacon pulses to the packets of randomness. Each pulse has a fresh 512-bit random string. Each pulse is indexed so that you can refer to pulse number 37 at time noon on a given day, and it is signed. And then any past pulse is publicly accessible, and the sequence of pulses forms a hash chain. Now, this can have several uses, but doesn't necessarily solve everything. Types of things that it can be useful for is to enable public auditability of randomized processes, coordination between many parties, and prove that something has happened after a certain time, namely after a pulse has been issued. But this is not good for selecting your secret keys, for example. So some of the type of applications that we conceive for randomness beacons or public randomness issued by a randomness beacon would be applications where it may be useful to prove later in time that randomness was properly used. For example, in clinical trials, it may be useful for the public to check that the trial was properly randomized. In some cases of legal metrology, you want to make proofs of correct software possession, and by using beacon randomness, you can ensure that you can bound the proof to a particular random value of the beacon, and that allows you to prove that the proof was performed after a given moment in time. In other cases where, for example, you want to select a public official for an audit or a judge to judge a particular court case, it is useful to have a procedure whereby you can show, look, this person was selected without any bias, and you can enable the public to verify that. And you can also use this for selecting samples for quality control, for example. Okay, so NIST has this project called Interoperable Randomness Beacons. In particular, this project has deployed the beacon version 2.0 in 2018, and since 2019, we've called this project Interoperable Randomness Beacons, namely to enable us to differentiate various tracks within this project. However, the project has actually started in 2011, and if you look at the web page for the project, you can find various historical notes. Just for a brief overview, what this project attempts is to promote a reference for randomness beacons so that others can use that reference. We maintain a particular NIST beacon implementation. We promote the deployment of multiple independent beacons. We would like to promote applications of beacon issued randomness, and we also support complementary initiatives about trusted randomness. For example, certifiable quantum randomness. Okay, so this was a brief introduction about the project and the scope. A little bit about the beacon reference. As I mentioned, this is a reference that is described in a report, which is still in draft mode. Some topics of this report include specifying a format for the pulses, describing beacon operations, for example, promises about the timeliness of pulse generation. It describes how, at a basic level, how beacon randomness can be used for various purposes. And it has a number of security considerations about how trustworthy a beacon like this should be considered. Let me point out that this has been a draft for a very long time at this point. It has served the purpose of supporting the development of various beacons, such as the one in the US from NIST and also in Brazil and Chile. We do expect an upcoming revision that will actually specify version 2.1, so it will introduce a few improvements along with the open source code. At a very high level, what a beacon does, according to our reference, is that it produces pulses at given moments in time, and then it makes those pulses available to a database. And then that database can be queried by users that can query the latest pulse or any past pulse for that matter, and some other metadata as well. So here's an example of a QR code and a URL where you could fetch the latest pulse from the NIST Randomness Beacon, and the beacon specification specifies an API whereby you can obtain different types of information. This slide is just, I'm not going in detail into it. This is just to show you that when we conceive the randomness beacon, we conceive a number of different modules, different parts that work together while also conceptualized separately. And this allows us then to make an analysis where we can ask what happens if the time service gets compromised, or if the HSM that is supposed to sign pulses also gets compromised. And then we can make a security analysis where we provide different guarantees depending on how the system together is working. Let me point out here that in this example, we have 3 random number generators, the third of which we consider optional. That is, for example, one feature of the reference. We require that randomness is obtained from different random number generators. Okay, but what is exactly a pulse and what is its randomness? Let's go into the pulse format. And because this is a very short presentation, I can't go into detail, but let me mention that a pulse, according to the NIST reference, is basically a packet with 21 fields. You can consider them each of them having a different role. So you have, for example, some fields that are mostly for context or administrative purposes. You have some pulses that relate to the signature, like a certificate ID and a signature. You have indexation fields so that you know which pulse we're talking about. We have the actual randomness, and in particular, let me point out, we have a randomness local value, we have a random output value, and we also have a pre-commitment value. I'll talk a little bit more about that. We have some fields for external values where we can actually input values coming from outside. Those usually improve some of the freshness guarantees. And also because we are hash chaining the pulses, we have a number of output values from previous times, not only from the previous pulse, but also from 1 hour ago, 1 day ago, 1 month ago, and 1 year ago. Okay, let me briefly focus on the random values in a pulse. So as I mentioned, there's a random local value, aka local random value, and there's a randomness output value. The local random value is essentially the SHA-512 hash of the concatenation of various random number generators. And this value is actually pre-committed 1 pulse in advance, meaning it is pre-committed in a pulse generated at that time, and then it is only released 1 minute after. And this pre-commitment is actually useful for the reason for its existence is to enable combination of randomness from different beacons in a way that it ensures independent values from different beacons. Then we have the random output value, which is essentially the hash of all previous fields in a pulse. This value is actually fresh at the time of release, and this is the actual randomness value that would be used by applications if you're not combining various beacons. This slide is just for visually hinting at what the various fields in a pulse. And now I can finally be in the part that I think is more interesting. Again, because this is a very short presentation, I just want to make a few selected considerations on some challenging aspects or some research aspects, or just aspects that are interesting to reflect on. Here's a note on the use signature scheme. So one feature we need from the signature scheme in our construction is we need the signature to be verifiable and deterministic. And this is so that we prevent bias of the random output value. So, we have our procedure for generating randomness, the local random value, but in the end, we need to sign everything. Well, a probabilistic signature, or even a signature that is deterministic, if built honestly, but you can't verify that, then we're actually allowing the value to be tweaked, and it's no longer following our procedure. Because of this, we are actually using RSA, PKCS version 1.5, which is the only verifiable deterministic signature that NIST has standardized, if we focus on stateless signatures. Now we could consider, could we use better signatures? For example, if we focus on BLS, it actually has better properties. It's succincter, it's verifiable deterministic, but it's not NIST standardized. So again, for that matter, we're using RSA. What would be an ideal case? We would like a stateless signature that is post-quantum secure, is verifiable deterministic, and why not even threshold friendly, so that you can actually implement it in a way where the secret key is not at any particular time. We don't have that, so this is an open research. And as an alternative, for example, we could also consider conceivably NDSA or Schnorr if we would put along an extra field with a ZK proof of determinism. Anyway, moving forward on properties, we are interested in timely combination of randomness from various beacons. What should you do if you don't trust any beacon in isolation? Let's consider two cases. Let's assume you have two beacons with the same period. Then one of the guidelines we have in our reference is that if you want to use two beacons, then you can receive their pre-commitments before they release the corresponding pre-images, so that you're sure that one beacon is not waiting for the other to release their value. Once you've received that, then you can actually obtain your randomness, this RT, as a hash of the previous values and the current value, and this will allow you something that cannot be tweaked to the advantage of a malicious beacon. Now, what to do if we have beacons with different periods? This is actually something we don't consider in the current reference. I just want to mention again something more from the point of view of conceivable tweaks or research. Well, a conceivable enhancement is that you can actually let each pre-commitment, or at least some selected pre-commitments, gradually release various pre-images. Just imagine that this pre-commitment is generated as a nested hashing of some randomness. So for example, if you want now to reveal something only after having pre-committed within 1 hour instead of 1 minute, which is the period of the NIST beacon, then you could consider something like at 10 a.m., you will reveal the hashed pre-image of the pre-image of the 9 a.m. pre-commitment. Again, I'm just mentioning this to mention that there are some interesting problems still to be resolved from a perspective of implementation and applicability. Okay, very shortly to start wrapping up. In the future, very soon, we hope to publish the upcoming revision of the NIST reference, which will contain version 2.1. And there are some considerations of things that we could promote in the future. So for the upcoming revision, we have a revised API. In particular, it will allow better filtering of pulses. We want to support multiple simultaneous chains. And we also have clearer requirements, such as related to timing and some aspects of the status values that we also specify. For the future, we expect to implement external values. It's something that is in the specification, but which we have not yet implemented. And this allows possibly to interleave or even hash chain, in a sense, values from different beacons. And this will allow us to have better freshness assurance. We definitely want to promote applications with publicly auditable randomness. And in terms of guidance, it will probably be useful to actually issue some written guidance on how to use and combine beacon randomness and how to enable auditable applications. Concluding remarks, randomness beacons do have a great potential to serve as a public utility. We believe that further guidance and promotion is needed. And please stay tuned for the upcoming revision of the reference beacon. I put here in the final slide just some links in case you're interested. And thank you very much for your attention, and I'm open to questions.
Oh, thanks a lot, Luis. That's a great start. Any question? I think we can take a couple.
Yeah,
Or
there
if
is a
not,
question by Don Weaver.
Okay. So do you see? I don't see. Okay, it's somehow it's
Can you
hidden.
see, or do you want me to?
Oh, I just see it.
Oh, I can see now.
Yeah.
Okay, so the question is, does NIST have efforts towards standardizing decentralized random beacons? There are 2 papers later today about this topic. Let me point out, the closest effort we currently have about decentralization is the NIST call for multi-party threshold schemes. Actually, the submissions are the final version will be published soon, within the next couple of months. And it has a submission deadline for abstracts for later in the year, and then actual proposals early next year. And this will actually allow NIST to analyze a number of decentralized protocols. So I think that's a very good start. VRFs, as mentioned here in, again, another question, is what we call a possible gadget for these systems. And I think this effort will likely lead NIST to be more aware of possibilities of decentralization. I would say, for example, in the scope of the NIST Randomness Beacon, it would certainly be an interesting development to, for example, implement the signature in a decentralized fashion. And by the way, one note that I actually didn't mention in the presentation, but I think it may be relevant in the scope of this workshop, is that this project of the NIST Randomness Beacon is basically an attempt since 2011 to call the attention of the community for the possible importance and utility of public randomness. So really the goal of even having the NIST Randomness Beacon and this reference is to really promote that other entities also build their beacons, and then they themselves can make possible different experiments on how to actually implement their systems.
There is one question, regarding the slide being publicly available. I think some version of slide will be available, but we'll also make the recordings public.
Yes,
Yeah.
and I have some bonus slides here, just browsing through them now, but most of this is actually in the reference. When this is offline, feel free to look at it, but this would be impossible to cover in this presentation, so I put it in the end. And feel free to reach out, anyone.
Yeah, I think maybe one more thing will be, because the people who are giving talk will be always available, so you can keep typing question, and maybe Luis can still answer them asynchronously once he sees the question. So please keep typing question. But while you're doing that, tag the speaker, like who the question is for, so that then otherwise other speakers do not get confused. Okay, we'll keep the question and answer open, and please continue to type your questions there.
Thank you very much.
All right, then I think, okay, there is one more question. Is there a slide summarizing the randomness schemes for VRF based? Okay, I guess so. We'll see if the slides are public. All right.
It is not VRF based.
Yeah, this one is not VRF based, but I guess we'll see some of them in later talks probably. All right, so I guess it's time to move on. Great, thanks a lot, Luis. And we have our next speaker, Patrick McClurg, who is a CTO at Randamu. And when I met him last time, he was working at DRAND. So he's going to talk about DRAND. Its title of the talk is Operating the World's First Threshold Network for Fun and No Profit. Amazing. Okay, over to you, Patrick.
Thank you very much, Patrick. And thank you, everybody. It's nice to see so many colleagues in this space again, and some familiar faces. And thanks, Luis, for your talk. It was wonderful. Also quite fitting, as the last talk was about randomness beacons and the standardization from NIST. And my talk will be about operating a randomness beacon, in fact. So a little about myself. I'm the CTO at Randamu. Randamu is a company focused on threshold cryptography and in part in randomness. And we are the stewards of the DRAND project. And the team have been working on it for the last couple of years. Yeah, keep it up and running. So what is DRAND? DRAND is a threshold network for generating unbiased, verifiable random numbers as a public good. So to break some of this down a little, a threshold network refers to threshold cryptography, essentially a set of cryptographic schemes that involve sharing trust between multiple participants such that you require some subset or threshold of them to work together in order to act on behalf of the group. Generating unbiased, verifiable random numbers. I think Prache mentioned in his initial talk, but that's the topic of the day. And a public good is in relation to the fact that DRAND is open to the world, it's free to use. It's a bit like water, that you don't have to pay to use it. It's open to everybody. We don't, other than some rate limiting naughty services, we don't deny anyone the access to randomness. In fact, it's conceptually a little bit similar to NTP, the network time protocol. So at the top of the diagram here for NTP, we see clocks. In the case of NTP, these are atomic clocks littered throughout the world. In the case of DRAND, this is a couple of core services running the DRAND protocol that generate the random numbers that are verifiable, and they get relayed out to different protocols, including libp2p, HTTP, onto different blockchains by different parties. And given the numbers are verifiable, anyone can receive some DRAND randomness from any party, whether trusted or not, and be sure that what they're getting is valid. How does it work? First off, nodes in the DRAND network perform a distributed key generation protocol. This relates to the threshold cryptography I talked about a moment ago, but in essence, they do some multi-party protocol such that they all get a small share of a shared private key, but no single node ever has access to that private key. It doesn't live in memory. They never see the entire thing. So as such, they can only act on behalf of that private key when they work together with other nodes. Another key point here is that all the entropy that ever exists in the DRAND network enters the system here. And in fact, all future random numbers are determined at the point of distributed key generation, which seems counterintuitive that we could have random numbers from the future that are predetermined at this point. But because nobody has access to private key, nobody can predict what those numbers are going to be. Then every time we want to create a random number, all the nodes in the network use their partial key to sign a message, gossip it to all the other nodes in the network. And then once a threshold number of those nodes gather partial signatures, they can aggregate them into one final signature that's valid for the whole group. A key point here is that any subset of those nodes that reach this threshold will come up with the same signature. In an alternate world where our threshold was a very small number, let's say we had 100 nodes and our threshold was 3, every group of 3 nodes will come up with the same signature, even if they can't talk to one another. It's mind-blowing. So to that end, DRAND signs an integer every round. That's the message that's being signed. It's predictable, i.e. it's monotonically increasing. That is, it increases by 1 and never decreases. And each of these rounds map to a precise time on the clock. So we can think of DRAND a bit like a cryptographic clock that ticks with these pulses that Luis mentioned in his last talk. So who runs it? This is about running the world's first threshold network after all. It's run by the League of Entropy, which is a global DRAND network run by a consortium of different organizations across a lot of different spaces. Web2 companies like Cloudflare, Web3 companies like Ethereum Foundation, Protocol Labs, universities like École Polytechnique Fédérale de Lausanne, UCL in London, a couple of other Web3 companies, multiple ISPs. In essence, we try and keep a wide range of different stakeholders in the League of Entropy such that there's never an over-concentration in one particular group. So the League of Entropy was founded, in fact, by Cloudflare in 2019. And since then, it's grown quite a bit. It's now, as of very recently, 27 organizations between testnet and mainnet. In mainnet, we've got 21 nodes. We still some have to graduate from testnet, as it were. We've been running for 5 years. In fact, it's the 5-year anniversary of the League of Entropy this week. Get the party poppers ready. In that time, we've actually had 0 disruptions in mainnet, which is a testament to the resilience of threshold networks compared to traditional centralized services. And we operate nodes in 11 different countries. Some of the pie charts here on the left might not be entirely accurate, but in essence, we cover a lot of the world. And the network's permissioned, which to some of the decentralization acolytes here might seem like a bad thing, but in fact, it ensures that we don't, for example, have too many nodes in any given cloud provider. So we try and accept new members to the League of Entropy, keeping that in mind to ensure that lots of people have it on-prem, all the different cloud providers are covered, and a range of different countries are covered. And as a result, yeah, no downtime. So it's pretty nice. Some cool stuff that people built on top. There's actually loads. I haven't captured it all here, but some highlights perhaps. Very recently, one of our community members, Kevin Charm, released Lotto PGF, which is live on, I was going to say Ethereum, but actually I think it's Arbitrum. So yeah, they in fact implemented BN254 scheme for DRAND because BLS12 isn't available on EVM blockchains yet, but they do a lottery for public goods funding. So if you want to save the planet and do a bit of gambling, invite you to get involved in Lotto PGF, although that's not, I'm not promoting gambling, so just saying if you're into that kind of thing. On the bottom left, we've got Filecoin. So DRAND, the biggest user, in fact, is Filecoin. It's used for leader election and challenging storage providers on proofs. So part of their core consensus protocol. Games, one of the hot topics of today, Pirate Nation from Proof of Play uses DRAND both on and off chain, in fact, to do some very cool PvP protocol, which their head of engineering, Matt Fan, has talked about at a few conferences. I encourage you to go and check out some of his talks on how they've combined different sources of randomness in order to make PvP play fair, which is quite cool. Sui and top, they released a time capsule built on something else I'll talk about a bit later, which basically allows encryption to the future. And at the top there, social income is a not-for-profit that provides universal basic income for, at the moment, the poorest people in the world. So in Sierra Leone, so donors throughout the world donate 1% of their income, and that's dispersed to the people who are most in need in Sierra Leone. They use DRAND to select who receives that income because, of course, they don't have enough money to give to everybody in the world, as would be the point of universal basic income. And in fact, they don't have enough money to give to everybody in Sierra Leone. Yeah, they get lists of the poorest people from NGOs, and they use DRAND to select fairly people to receive basic income. So I encourage you to check them out. If you've got a bit of spare cash, chuck it in. And the final topic here is time lock encryption, which I'm going to talk a little bit more on. Time lock encryption is what it sounds like. You can encrypt something now that can't be decrypted until some point in the future. A lot of proof of work-based schemes were created in the 90s and 2000s to try and solve this. But given that we can't predict what kind of improvements in hardware will happen or fancy maths, they basically didn't work out. Given that DRAND is a cryptographic clock, it could possibly be used in a cunning way here to enable time encryption. How does it work? It's quite simple. Just lots of fancy maths. But okay, we're not going to get too deep into this because this looks too spicy for my ilk. Recall, DRAND rounds map to a precise time. And as a part of that, we know what future messages are going to be. We can tell that around 4010, the network is going to sign the number 4010. And we can exploit a property of pairing-based cryptography that basically we can move some parts in our big equation that we saw a minute ago, and we can turn the round number, the message we're signing, into a public key, and the signature over that round number will become a private key. And given that DRAND won't emit that signature, i.e. the random number, until the future time has passed, we essentially lock some ciphertext until DRAND's emitted the randomness. We actually built a vulnerability disclosure tool on top of time lock encryption, which I encourage you to check out. When you find a killer vulnerability in Adobe software, even if they send snipers after you, the world will know what you found. They can't take you out. So this is a dead man decryption tool, you might say. You can also do some arbitrary text encryption, decryption, so files and some other cool things. So I encourage you to have a go. So running any publicly accessible project, particularly a public good, has some tough bits. It's not all sunshine and rainbows like the rest of the presentation would have you believe. So some of the tough bits, actually the hardest bit's getting everybody out of bed. So the distributed key generation process, at least up until recently, and required all the node operators to sit at their computer and run a command to share their key. As you can see, I've plotted some dots on the map here from where we've got nodes, and it basically spans the entire planet apart from Australia and New Zealand. So if you're from New Zealand, Australia or New Zealand and have some spare compute, please let me know. But yeah, no time's particularly convenient for anybody. And yeah, particularly getting nerds out of bed to run a command is very hard. Our poor West Coast members have a hard time. So that's actually one of the biggest challenges. We've been working for a long time to enable distributed key generation that happens over a period of days or weeks, such that people don't have to be online to run these commands, which is coming very soon with V2. So hopefully this will be alleviated. The second issue is dealing with naughty spammers. I think most people who've run any popular public-facing network may have faced this, but sometimes spammers aren't even malicious or intentionally malicious. We can see here in the graphs some of our CloudFront metrics. We see 38.9 million requests. I think I want to say that is per hour. So that's quite a few requests. And in fact, we discovered that it was someone had just misconfigured the node and they were requesting the max int round. So perhaps somebody was doing some funny math somewhere, reducing or decrementing rounds and got the max int or something, not sure. But anyway, that cost us thousands of dollars in CloudFront bills. Yeah, Daddy Bezos has been fed by the DRAND machine, unfortunately. So we eventually moved off CloudFront. Additionally, incentivizing community contributions is quite hard. We're an open source project. It's a public good, but it's also a fairly complicated project. We've been running for a long time, and we can see 2 core contributors in top here naturally. Dependabot is actually the 4th biggest contributor to the DRAND project in the last year. We output lots of learning material and such. Again, Luis touched on this in his talk about releasing learning material, tutorials and stuff to help onboard people. And we do a bit of that, but of course, there's so many cool projects people could work on. It's quite hard to tempt people into working on yours versus something else. But if you're a gopher, i.e. you write Go, we'd love to have your contributions. So what's next for DRAND and for the League of Entropy? Firstly, please give us the BLS 12 3.1 precompiles on Ethereum. Allegedly, they're coming soon in the next upgrade. For those of you who are not aware, I mean, BLS 12 3.1 is the signature scheme which we use to create DRAND beacons. Not available in many blockchains because Ethereum back in the day went for a different signature scheme, alt BN128 or BN254, which kind of got pwned at some point, but they haven't upgraded yet because upgrading a public decentralized networks hard and slow, and you have to be very sure when you make changes. So this EIP has existed for quite a while now, and fingers crossed in the next Ethereum release it will actually happen, and then we can have convenient, fast, cheap DRAND on EVM blockchains. Go and hassle your local Ethereum evangelist. Hopefully, NIST standardization will come soon. We've been keeping an eye on the interoperable Randomness Beacon standard. We are Randomness Beacon, although some of the tenets of it are a little bit hard for us to implement because, as alluded, I think by Mr. Beaver in the chat, that we're distributed Randomness Beacon, so it doesn't match exactly. But tied to that, we've got the multi-party threshold schemes draft NIST spec. So hopefully that will unlock a whole world of possibilities that we can leverage. And together, maybe there'll be a decentralized Randomness Beacon standard. And I hope that DRAND will be at the forefront of that. Also, recently, the DRAND project received some retro PGF. For those of you who don't know, retro PGF is retroactive public goods funding. It was a movement, you might say, started by Optimism a while ago. Basically, the concept of anytime you raise a big bucket of money, you commit some portion of it to paying things that happened in the past. So the Filecoin network recently did a retro PGF round, and the DRAND project received just over 4,000 fill, which unfortunately, looking at today's coin market cap, is probably not very much, but we're going to plow that into the League of Entropy and hopefully do some cool new things. And that is everything I've got. I'm a little ahead of time, so I'm happy to take any questions, but some calls to action for you guys and girls and everything else. If you have some spare hardware and you're experienced running production grade systems, League of Entropy is always looking for new members to join. So if you're interested, feel free to email me at have an email address or drop a little tweet to the DRAND's Twitter. And yeah, thank you very much. I see a red icon in the Q&A box. Let's see. Oh, they've both been answered. Wonderful. Are there plans for a Rust version? Yes. In fact, we had one of the League of Entropy members, DoorSwift, did begin a Rust implementation and presented, in fact, at the League of Entropy Summit in Istanbul last year, although it's been a little bit silent on that front. So I don't know what the status there is, but yeah, ideally in a future world, we would have at least 3 implementations such that any bug affecting one of them wouldn't take out the network. But if Aditya, if you'd like to start one, I'd love to get involved. A question from Kostas here. Do you ever have any sync issues in QuickNet? Are you not able to produce a beacon on time? And if it happens, recovery implies that nodes compute all missing beacons before catching up. Yes, this is a good question. On the catch-up side, we actually have a rate limit, you might say, on catch-up that we set for different networks. Because, of course, if a network goes down for 24 hours, for example, you might have to produce a lot of beacons very fast, and that could flood the network. Generally, we set catch-up period to be half of the beacon period, i.e., if the beacon period is 10 seconds, then catch-up will happen every 5 seconds. So that means it would take 12 hours to recover, more than 12 hours, but 12 hours to recover from a 24-hour outage, of which there haven't been any. In terms of beacons not being produced in time, yeah, it certainly can happen. We haven't had any massive timeouts in that regard, at least not mainnet and testnet. That has happened occasionally, but BLS signatures are comparatively slow compared to some other schemes. So we find on average beacons get emitted around 500 milliseconds after the on the clock time for when they ought to come out. We're investigating different ways to get around that, like pre-generation of some of the signatures, etc., aggregation without verifying the signatures optimistically, some other things. I think there are some possible ways around that we're investigating, but we haven't got any concrete implementations there just yet.
Yeah. So
Right,
I
so
guess
there
Luis
was-
also had a question, but maybe Luis, you can just pick up. If you are on the panel, then yeah, even I can't
Yeah.
ask question by typing. Luis, please. You can,
Thank you. But let me start by saying I was actually trying to ask a question, but mistakenly I answered the question of somebody else. So that question is still lingering. I put it on the chat. I don't know. It was from Hussein.
Yeah, I
don't
can
know if
read
you
it out.
see it.
I can read it out. Concerning time locks using randomness to be generated in the future for encrypting something right now, how does it work? It's a question by Hussein Hafizi Mukhaddas.
Yeah, so it's the simplest way of thinking of it is that we had this big equation for pairing-based cryptography, and as long as both sides of the equation balance, as it were, everything works out. So we can exploit this pairing nature, the commutative principle, that we can basically turn some message that we're going to sign in the future into a public key. So I can encrypt something using this message and the signature over that message as a private key, such that whenever the DRAND network emits the signature, which constitutes randomness, then I can use it as a decryption key for my ciphertext.
Yeah, so maybe I can add one line here. So the idea is to use some sort of identity-based encryption where identity is not defined, it is a future time. And that's a whole sort of idea of identity-based, that the public key is not known ahead of time. So you just encrypt to some identity, and identity is your future time. So that's our overall idea here. Anyway, okay, so Luis now has his question. So Luis, you want to ask? They were muted, Luis.
Thank you, Patrick, for the nice talk. I actually have a couple of questions, if there is time. The first one is a bit slightly more technical. So in DRAND, the entropy is defined in the beginning, and
Correct.
then the future is unpredictable, but it's gradually released. Is it conceivable that, and I'm asking this as a feature, not as a vulnerability, is it conceivable that a DRAND chain would allow input of external random values at given points in time as a way of tweaking what the future randomness will be, and in a certain sense improving freshness if some application actually requires freshness?
So in principle, it is possible. The issue for us is that it changes then the public key of the group, where you have to somehow publish this randomness out of band. For a lot of applications, that's untenable because you want to pin the public key when you first start using it, and then ensure that you then would need to keep track of any of this randomness that's injected at other points. But it is in principle possible.
Okay, thank you. Yeah, I'm imagining that it would probably hinder a little bit this time lock functionality, which is really cool. But on the other hand, I still think about it as a bit of a research problem. There might be a way in which, as long as you can keep state of what has been inserted, somehow still enable that, if that thing that has been inserted is somehow vouched by a quorum. Anyway, that was just a comment. The other thing, it's a little bit of a comment, maybe considering the two presentations. I just wanted to say that I think a significant difference between the DRAND and the NIST Beacon is this aspect of when randomness is generated. So again, DRAND generates in the beginning and then gradually releases, and it does enable a number of interesting features. NIST has this, the way it's built is that it actually wants fresh randomness. But that said, and despite of that creating some aspects of interoperability, I think there's actually a lot of room for possible nice things to be done together. Maybe the simplest example would be to use external values. Let's say in the NIST Beacon, we can actually use DRAND values and leverage the joint, having a better assurance from the two combined beacons.
Absolutely. Yeah. Thank you, Luis. I think Costas had another question there. Yeah, for new to SIG, is it a requirement that should always see the previous round before doing so? Actually, in our initial scheme, we had that. So we had this concept similar to the NIST Beacon where each random value was linked to the last one. We found that it didn't increase security, and in fact, it made time lock encryption impossible. So now every beacon stands on its own, so it's statelessly verifiable, which also means it's actually faster to verify.
Alan has one question, if you want. Shall I read? Or
it looks more like a comment than a question.
Okay.
Let's see. From Tarak, though, how often do you run a DKG on mainnet, and what triggers it? Right now, we run a DKG every quarter, approximately. We basically use it just to onboard and offboard members. Yeah, we can do it more frequently if we have lots of membership requests, and do it less frequently if we have fewer. Again, new entropy enters the system when we do a resharing, so it's not really a security thing whether we do it more or less often.
I guess that's it then. Okay, Alan's comment, maybe I should just read out. So if you need to catch up faster, each replica in DRAND could produce a batch of the signature shares, and then aggregation of all the shares could also be somewhat faster. Yeah, I guess that's correct, right? So you agree with that, yeah. So Costas has one more. I think it's already been answered. Refreshness that not allow for time lock, because you need. I think it's the joint question. It's explained two things. All right then, great. So thanks a lot, Patrick.
Thank you.
Great talk, great discussion. So now we have Jacob from our own giving a talk on findings in deployed service, and we've been researching on different deployed services and what an ideal randomness service on chain looks like. So I guess over to Jacob, please. Yeah.
All right. Can everyone hear me okay?
Yes.
Sure.
All right. I see some nods. I hear some yeses. Awesome. And can everyone see the PowerPoint?
Yep.
Awesome. All right. Then I'll get started. Thank you to Luis and Patrick for your awesome presentations. And I think that'll actually maybe let me speed up a little, because there's a good amount of background on beacons you'll have already given today. So I'm excited to get into this. We're going to be talking about security considerations for on-chain services, on-chain randomness services. And to start, I'll just give you an overview of what this presentation is going to contain. It's going to contain some necessary background about randomness in Web3. Then we'll talk about specifically randomness for dApps. We'll talk about deployed services that are currently available, their pros, cons, securities, insecurities, advantages. We'll talk about some additional considerations that may apply to some or all of the deployed services, depending on their type, such as if they're VRF-based, beacon-based, etc. And finally, we'll have some time for questions. So let's get into this with some background. So randomness in blockchain. It's a very important aspect of blockchain. It's used for consensus, cryptography, video games, lotteries, NFTs. These are all important places where we need randomness, but we want to narrow down our conversation a little. So for consensus, the randomness is generally generated and consumed as part of the protocols. For like example, validator selection. You'll have with each block, each round of the protocol, you end up generating new randomness for a future round. So that's not really what we're interested in. That's been rigorously studied. That is part of the consensus protocol. There's cryptography, and these are frequently used for off-chain calculations, such as Schnorr proofs, ECDSA signatures, encryption. And in these cases, using bad randomness really only hurts the party choosing RAND. If you don't choose a good source of randomness, you're gonna maybe reveal your secret key, or maybe someone will be able to figure out what the message you encrypted was. So it's really in your own best interest to choose good randomness, and this randomness is never published anywhere. So we're not really interested in that either. That's just in choosing good randomness yourself. But we're interested in these three, which we could classify as randomness used for on-chain dApps. Blockchains don't generally natively offer video games or lotteries or NFTs. You have to program them. They're in applications that are run in a decentralized manner. So let's get into it a little. What are dApps and smart contracts? Basically, they're programs that are deployed on blockchains. Transactions are formatted as function calls, so a client can interact with a dApp by submitting transactions. So for example, they could call mint NFT or play game. And the most important thing to learn here, and the most important piece of the background, is that these blocks and these transactions are executed deterministically and sequentially. And there's a reason for that. If you think about consensus as, in its simplest terms, a way for everyone to agree on an ordered list of transactions, we want to all agree on the state. So if we're all in the same starting state and we have a list of function calls that we want to execute, we want to be in the same state when the protocol ends. My cat is getting in the way. I don't know. Yeah, she's invisible. Sorry. But yeah, they need to be executed deterministically and sequentially because we want everyone to agree on the state. If we're using randomness in our execution, then even though me and you agree on the list of transactions, we'll have a different state at the end. And that gives the block proposer a lot of power. If I'm a block proposer in a proof of stake system, I could potentially propose 2 or 3 different blocks, simulate the execution entirely, and pick the one with the output state that favors me most. So these last 2 points are the big takeaway of the background. That blocks are executed deterministically and sequentially, and that because of that, the block proposer has a lot of power. So what's our motivation? As we said before, our goal is we want to be able to access randomness for Web3 apps or dApps. And so let's give a simple example. We want to mint an NFT and we need a random number from 1 to 10. We'll make it 0 to 9 to make it easier. So on a 0 to 5, you have a 60% chance of getting the common, the normie no coiner. You don't really want to get that guy. No one wants to get that guy. You have a 30% chance on a 6 to 8 of getting the Chad whale. I'd be friends with him. You could get the uncommon. And you have a 1 in 10 chance of getting the rare, the Giga Chad 8. That's the one everyone wants. So in Web 2, whether you have a video game with item drops or some kind of collectible card game, you just have a trusted server who would pick a random number. So in this case, they would pick R equals RNG mod 10, and they would just have the appropriate logic. Here, the example would be mint NFT, R is equal to RNG mod 10, and then you have the logic to mint the appropriate NFT. Simple enough. But such an RNG call simply cannot exist as a function in a smart contract. This RNG function, while it could be executed locally, can't really exist in a traditional blockchain because the blocks are executed deterministically. If there was a function RNG that you could call in your smart contract, then the block proposer would know what that RNG result is. They could propose 3 or 4 different blocks, pick the one that gives them the RNG they want, and use that one, submit that one for validation. So that's where publicly verifiable randomness comes in. This is the problem we want to solve, that in Web 2, you could simply just call your local RNG sample for whatever your local entropy source is. But for Web 3, we need publicly verifiable randomness. And that brings us to the meat of the presentation, randomness for dApps. And we'll start with our desired properties. Some of these may look familiar to you who are familiar with cryptography. We'll start with unpredictability. No one should be able to compute the output ahead of time. For a more rigorous definition, a probabilistic polynomial time adversary, there should be no probabilistic polynomial time algorithm that allows you to figure out what the randomness will be ahead of time with non-negligible probability. Non-negligible probability speaks for itself.
I think we lost connection, right?
Yeah, for some seconds. Last 30 seconds we lost.
Um,
Now back.
Perfect. So one question says RNG can exist as a smart contract call if you do it carefully. There are trade-offs. To answer that really quickly, you need a specialized consensus algorithm where you don't just have the proposed block is executed. You need to generate the randomness for each block after the block is finalized or after the block is validated. Aptos has experimented with that, but we're talking about traditional blockchains. That is possible, but you need a highly specialized consensus algorithm. But let's talk about the desired properties. We have unpredictability, so no probabilistic polynomial time algorithm should be able to allow us to figure out what the randomness will be ahead of time. We have unbiasability, so no one should be able to change the probability of a given outcome. And these two together make up pseudo-randomness. This is a classical definition. We've all seen it before. It's that the
I think
randomness
there is
is
again drop, Jacob.
Yeah, there is some instability. Yeah.
Yeah. Now we can hear you, I think.
I'm not sure what's up with my internet. I'm sorry.
Maybe
but
for a few minutes, you want to just maybe please stop your video. That might help just to while you go through the talk, and then you can, yeah, maybe.
Great call. Great call. So anyone should be able to verify the random number is provided is pseudo-random. The next probability is liveness, which we have a slightly modified definition. For DVRF, for example, we'll say that liveness is that you'll always get a response if at least some threshold of nodes is honest. We're talking about at a higher level here. What we want is that all requests are fulfilled exactly once with a valid random output. We're going with a higher level definition here. And then this last definition isn't actually part of the security definition, but in my opinion, it's one of the most important and least talked about aspects of these protocols, which is usability. The service needs to be intuitive and for the average Drupal developer. Clear standards for secure usage need to be laid out. If you have a randomness service and you need a degree in cryptography to actually be able to use it, then it's not very useful because the target for these protocols is for anyone to be able to develop a Web3 app, a dApp, using on-chain randomness. So that's one of the things that we'll see that separates this from some of the presentations you may have seen in the past. Usability is a key feature because it is very easy to misuse some of these services. So let's talk about the flow of Web3 randomness now. Really quickly, can you guys see my mouse?
Yes, we can.
Yes.
Perfect. All right, so we've discussed that this kind of RNG call doesn't exist. So how do we do it? We're going to need two transactions. The randomness is going to be computed off-chain and validated on-chain. And what that means is that we need a commitment to the request. We make the first transaction where we request randomness, and the second, so an example, slide. When we mint the NFT, instead of just having mint NFT, we mint NFT request and mint NFT fulfill. The request is assigned a unique ID, and we store the requester info. So this is something that was happening in the dot over here, but whoever calls mint NFT in Web 2 supposedly will get awarded the NFT. Since we are having two transactions, we need to maintain that state. So what we do is we save the requester info with respect to the request ID. Then someone will generate the appropriate randomness with respect to request ID. They'll generate the randomness in the proof. And then we have a few things we need to do. We need to verify the randomness, ensure the request has not yet been fulfilled. We need the logic to mint the NFT. We need to transfer the NFT to the wallet associated with it. And we need to mark the request as fulfilled. So only these two are really part of the client application, minting the NFT and transferring the NFT to the wallet. The rest of these are really things that should be handled by the randomness service. It shouldn't be on an average Web3 developer to verify the randomness necessarily. And we'll go into, there's a link at the end. We have an ePrint for it. We just submitted to Oakland a rigorous treatment of verifiable randomness as a service. So this is our first idea of what a randomness service might look like, but it's connection unstable. Can everyone still hear me?
I think we could hear you.
Sorry for all these issues. But yeah, so that's why we formalize this. So let's see what an idealized service would look like. Over here, we have the provider smart contract, and over here, we have the client smart contract. What we're trying to accomplish is we're trying to run some app. It does some things, do things. We request the randomness, or we generate randomness using local RNG, and then we do some more things. How can we have the equivalent of this in Web3? As we mentioned before, the client code is going to have to maintain state. supposedly do things will save some local variables that are used for do more things. So that's all state. So parts when ID by requesting randomness.
Yeah, now you were muted for 5 seconds again.
So we do some things. We make the request ID by requesting randomness, and then we save our state with respect to the request ID. And we'll notice that request rand takes config. At the end, we'll discuss there are lots of potential config variables, but for now, we assume there's only one. We assume that the only config variable for simplicity is the callback function. So we see that we're saying we're requesting rand, and we want that randomness supplied to the run app fulfill function. So when we call request rand executes, it generates the unique request ID, it saves the config for later, and it returns the unique request ID. So already we've moved some of this reusable code to the provider smart contract. So now the client doesn't have to do this every time. Now, though, we'll see for liveness, we actually have the provider call the fulfill rand function. We do the verification here. So we do close. So we're making sure the randomness is good, that it hasn't been fulfilled. We load our config to get the callback function, and then we perform callback. So in this case, callback would be calling run app fulfill, because that's the function we specified here. So we're already making things significantly simpler. From the client perspective, they're only calling one function, run app request, and then they wait for the provider to handle the rest. And eventually there will be a second transaction. So this run app from the client perspective is still one call. And then the run app fulfill, and instead of having to validate the randomness, we only have to validate that run app fulfill is being called by fulfill rand. And if it is, then we know that all of these checks have passed. So we load our state, we finish execution, and at the end, the request is marked as fulfilled. So this is our idealized service. It's a lot at once, but this is what we hope to achieve. Where did state come from? So where did state come from? So do things over here is simply when we function, and those variables supposedly will likely be used when we execute do more things. We'll say, okay, let W equal X plus rand, or something along those lines. So anything that is generated during do things that we need during do more things, we just save as local state for later. Yeah, so state is just a way of saying, okay, we're dividing execution in two. We need to save any relevant state between the two halves of execution. So this is what our idealized service should be. This is basically the minimum of what we could do. The client only has to save their local state. They have to request randomness. And all they have to do here is ensure the caller is their provider, and they have to load their state. So this is the minimum the client could do. And this is our goal. So let's see how that compares to some of the deployed services, which is the outer method. Okay, so that's the main idea here. Before we move on, is that which is
Jacob, you are again, we could not hear you.
So to answer
To
answer the current question, which is the outer method, shouldn't the same method have do things and do more things? That's the entire point of this slide, and the previous slide, is to show that they can't exist in the same function. We need a two-part execution because you can't have a single transaction for a randomness request, assuming deterministic execution of the blockchain. This rand equals RNG doesn't work. So what we need to do is we need to execute the first half, request the randomness, and then execute the second half. So this is two separate function calls. There isn't an inner and an outer function. There are 4 different functions, 2 on the client smart contract and 2 on the provider smart contract. First, the client calls the first function here. They run the app. Which calls the provider smart contract. Then the provider smart contract calls the client smart contract for the fulfillment. Happy to answer more questions. I believe I'm running a little behind, but they're the end, answering them along the way. So let's look at the first deployed service, which is Pith. Pith uses a commit reveal pair, which which means that the provider and client both commit to a random value, and then they're hashed together for randomness. So you can see here, the client chooses a secret S, and they generate a commitment, and then they save their commitment on chain, but their secret is still secret. And when they get the unique request ID, that lets them know what the corresponding commitment is from the provider. So I commit to my randomness, my secret random value, the provider commits to theirs, and then I'm able to later query them via Web2 to get the appropriate random value, and we could hash them together, validate both the commitments. But the issue here is that if the user doesn't like the output, if they don't like this hash of S, REQID, they can just choose to never reveal S, and no one can ever finish the game. So they can't guarantee liveness, which is a big issue. And another thing we'll see here is that the provider has to be blockchain aware. The provider should only return for request ID, return the value request exists. Otherwise, I'll query what this X request ID is and choose my commitment, my secret ahead of time to get the value I want. So there are several issues with this paradigm, several issues with commit reveal based VRF or commit reveal based randomness. We have VRF based. So a VRF, a verifiable random function, it takes a secret key and an input and provides randomness and a proof of randomness, that's the publicly verifiable randomness we talked about before. And we have the ability to verify that randomness. So the key thing here is that each request has to have a unique input. When we make the request transaction, not only do we get a unique request ID, but from the transaction, we're able to figure out some unique input. And it's important to note that input is biasable. The block proposer can rearrange the transactions. The request ID and the request input are totally biasable. But because of the properties of VRF, the VRF on that input is pseudo-random and publicly verifiable. So that's why we need to worry about replay attacks. We can't allow the same input to be used twice. The underlying security only for other inputs. If an input's already been queried, there's no guarantee of pseudo-randomness for VRF. So we need to make sure each input is unique. That's one of the key things here. And again, we have blockchain awareness because this input is biasable. If someone queries the VRF committee for an input that hasn't actually been existed yet, then I could learn what the random output will be and then make a request with that input. So that's the main drawback of VRF-based randomness services is that we need blockchain awareness. And the way we could accomplish this is with a relay committee. So this is how Supra accomplishes it. We have a decentralized VRF. So since we have the VRF on many blockchains, we have trusted relay nodes that basically they forward the request to the VRF committee, and that's a way to achieve scalability. Another way is that Chainlink increases the number of providers. They have multiple different VRF nodes for each blockchain, and that way each VRF node has to be aware of one block. And protocol also uses a VRF, but they have a complex architecture utilizing bridge. It's not even worth going into that architecture because they have some vulnerability to replay attacks. Lastly, we have direct beacon access. We already had 2 presentations on beacons, and while beacons are an incredible source of randomness, they fall into you need a bit of a cryptographic background to use them field. So we have, this part should look familiar. For each round R, we generate the randomness for that round, and we just set the beacon. We submit the round, the randomness to proof, and it's validated and saved. From the client perspective, they can get the current round, and they could commit to a future round. So let's say that there are beacons every 1 minute. I make a request at 12, and I say I'm going to use the beacon in 5 minutes from now. So get round will return 12 o'clock, or whatever the beacon number is, and get rand will be for 12:05, for whatever the round plus 5 was.
Jacob, you're muting for 10 seconds. Yeah.
So as we've seen in the previous presentations, an off-chain source emits a periodic random beacon. The client here is just provided with direct access to that beacon, and they're entirely responsible for safely using it. So the client needs to commit to config for any configurable variables. They need to initiate the fulfillment transaction themselves. And in some instances, for Algorand's documentation, it's not necessarily comprehensive. For instance, they say that in the event that a beacon is missed, it's up to the client to, quote, handle it gracefully. And the issue with that is that how do I know if a beacon is skipped? Maybe it's just a little delayed, and then the future beacon is more beneficial. There are a few issues with this, that it's putting the onus on the client. And to prove that it's difficult to use this randomness, if you look at XRandom's documentation, their sample smart contracts actually have several vulnerabilities. We're able to indefinitely delay the function from executing by calling down so that, and they also misuse randomness where you bias dice roll.
10 seconds.
Yeah.
10 seconds. Yeah.
We're running a little behind, point being that as evidence of this being difficult, even the sample smart contracts for how to use direct beacon access via XRandom have vulnerabilities. And one last issue, or I guess there are two more, is that we require a separate transaction for validating the randomness and for consuming it. So before, we had one callback function where we validate the randomness, ensure the request hasn't been fulfilled, and we perform callback. Here, we have 3 transactions total instead of 2. We have the request, the get round, we have the validation of the beacon, and we have the fetching of the beacons. This also adds latency. And finally, we're wasting gas because all beacons are validated on chain, even those which are not used. And that's not to say there are no benefits here, because the provider doesn't need to be blockchain aware. They don't need to be able to read the blockchain. They just need to be able to submit transactions. And that's a major advantage. So looking forward, we're actually hoping to publish logs soon. It'll last smart contract flow built on top of a beacon, but providing direct beacon access breaks that usability principle. It is perfectly possible to securely use a random beacon on chain for your DApp, but it requires a lot of knowledge from the client and is very error prone. So that's the main disadvantage here. For additional considerations, I'm actually going to skip some of these because we're running behind and I want time for questions. So the last thing I want to do is other configurable variables, just to show how much of this is handled by the provider smart contract. So all of these configurable variables are things that, for example, with direct beacon access would need to be handled directly by the client compared to with VRF or with the idealized flow, the provider smart contract handles it. So confirmation blocks or beacon delay, where if I want to wait for a certain amount of blocks, basically for finality, I could wait longer and say, okay, don't generate the output for my requests until 5 blocks have passed. Or I'm going to use the subscription info, such as who will be charged for the randomness, number of random outputs. This is actually where those smart contract vulnerabilities with XRAND come in, where as a cryptographer, you have to commit to how many random numbers you want when you make the request. And then you could say, okay, I'm going to hash over my random output with 1, 2, 3, all the way up to N. But that's something that can be handled by the provider smart contract. And finally, callback args. So what are our takeaways? The client should bear as little responsibility as possible. That's usability. That other point we didn't get to. But basically, if someone wants to launch an attack to bias or predict your randomness, it's expensive. And if you only have $2 gambling on this, it's unlikely someone will actually want to try to waste their stake to try to bias a $2. Commit reveal services can't guarantee liveness. Including block hash increases the cost of attack. We didn't get to that. And in VRF-based services, the VRF must be blockchain aware. So sorry for rushing. Thank you for your time.
Yeah.
Thanks, Jacob.
Yeah,
It was a little bit, I guess.
Sorry for
that connection. I guess it might be it keeps switching between different Wi-Fi's or something. It can happen sometimes. Hard to figure out. Anyway, it's great talk.
I'm not sure. I may have been a little ambitious with how much I wanted to fit in.
Yeah, that's always happens in the beginning.
So there are questions, Jacob. Yeah, there are questions. Somehow they got moved to the unanswered. I don't know.
There were a few questions along the way, but I answered those as we went because it would have been hard to go back to them.
Oh, did you answer while you're speaking?
Yeah.
Alan
asked a bunch of questions. I think it was already answered. Any further question from anyone? I guess we're pretty much doing pretty good on times. It's like just 10:30 Eastern. If not, I think we can end the session here. and we'll just take a 15-minute break. When we come back, we'll have a panel for you, like industry focused panel that will discuss. Okay, let me share my. So just discuss different aspects of the demand side, like what are the use cases, the best use cases for which randomness is required in the Web3 space. All right, guys. So let's join back in 15 minutes, 10:45 Eastern. Thank you.